Good idea. And delete the other one and focus on this. So any questions so far? So we already did it. We already reviewed all of this. We stopped here. Yeah, that's right. Any questions so far? Relative permeability, yes.
We discussed that we have for two cases, I'll get the third one. Do we do that for each step or one time?
What
each time of calculation or only one time?
I'm not sure I understand your question. Can you repeat the question?
So relativity for K for oil or for gas. We have one value only, or we have to create a plot in the simulation.
You need a real term section where you will provide saturation, say saturation of water, KROW, KROW is relative permeability to oil in the presence of water. KRW is just for water. That's it. These two will be, and then PC, OW. This will go together. This is one table. And then you have another one if it's three-phase. If it's three-phase or water gas, then you have another one with SG as the primary variable. KROG, relative permeability to oil in the presence of gas, and KRG.
And SW
and then PCG.
Saturation in general will be functional. PCG or PCG, for example, will be functional.
What's your question again?
Saturation will be functional.
Saturation?
Yeah.
Is a primary variable.
So it will be global, like variable.
Yes, you are solving for saturation. All these other guys are functions of the saturation.
So saturation will be at an input.
At initial conditions, yes, just like pressure. Just like pressure. So you need to get saturation distribution, and that can come from leverage J function. The petrophysicist can give you that, or you can assume it's constant everywhere. Above, below the water oil contact is 100% water, and above, you will need to use some density. So there are some tools they run, MWD tools, but basically the concept that's typically used is to use the understanding of, I don't want to make this a reservoir engineering class, so I don't want to go too deep, but you know that if this is the water oil contact, this is the gas oil contact, you know that the density below the water oil contact, this is depth, right? And this is density. The axis will be up, but I'm just going to put it down here. This is density. So what's the density for water? Yeah, it has a slope of, if it's in PSI per foot, 0.4 something, right? So you will draw that slope here. Below the water oil contact is 100% water. Above it, you can have water and some oil, right? You have residual water saturation. So what you will do is you will keep this slope for water. But you know that density is, pressure is rho GH, right? And that's what you've converted into pressure over pressure gradient is the rho G, which is the 0.45 that you said. So basically you will see that capillary pressure is basically related to the densities. And so this other guy will be here, a different slope for oil, typically lower than that for water. And you can convert these slopes to capillary pressures, which will give you the saturation. So you can get the saturation from the capillary pressure. And then when you get here, it also splits gas is steeper than this. You can review this. This is actually discussed in Eclipse technical documentation. If you want to get into this, Eclipse 100 technical documentation. But that's if you're actually working on a real field. For the purposes of the multi-scale simulation we're going to be doing, we won't go into that much of a detail. But yeah, technical documentation of any commercial simulator will be the best source of information for initialization. Spatial discretization schemes. So you already know. What are we discretizing here? There are two types of derivatives in the governing equation we've seen so far. What are they? Space and time. And then the one with respect to time, is it first order or second order? First order. And then for the spatial derivative is what? So which one are we differentiating here using these schemes? So can you use finite volume to discretize the mass accumulation term? No, it's for the spatial derivative, but finite difference can be used for both of them. And we always use finite difference for the time discretization, regardless of whether you're using finite element, finite difference, or finite element, finite volume. So I've listed out some simulators that use these different discretization schemes. Some comments on each of these and some of their pros and cons. This is limited to block structured meshes, of course, and extend it like it's done in these commercial simulators to work with corner point grids, which will always have 6 faces in 3D, but those faces don't have to be perfect cubes. You can pinch out, you can have these kinds of shape. It just has to have 4 sides. It does not conserve mass locally. That's why it's being phased out and replaced with finite volume method. Finite volume method is an approximation of integrals. First thing you do is to integrate the continuous form of the equation. It's mass conservative by construction because you're integrating over control volume, and the control volume will be each grid block in the domain. So it's locally mass conservative. It also conserves flux across the interfaces between each of the control volumes. It works for unstructured grids. So your grids can have any arbitrary number of sides. It can be 4 in some places, it can be 5, it can be 7. And that allows you flexibility to conform to different discontinuities in your domain, like fractures, like channels, like different material interfaces that don't have to be straight lines. So that's the advantage of using unstructured meshes. Locked or structured meshes will not be able to conform. There's no way you will be able to mesh this fracture, these 2 fractures, with Cartesian grids easily, right? You can't make the grid blocks conform to both fractures. If you choose the grid blocks to conform to these guys, and you're meshing it this way, well, you will have a problem meshing another fracture at a different angle. But with unstructured meshes, the meshes can change shape to conform to your fractures and faults and whatever discontinuity you have. Finite element method is even more flexible because triangular meshes have been shown to be more flexible in conforming to irregular boundaries, irregular discontinuities in the structure. So it's very good for unstructured meshes. We can use triangular meshes, we can use quadrilateral meshes. So that's why it's remarkably flexible and general. It uses something called weighted residual. We're not going to talk about finite element method. I used to, but I think it just gives us something more to worry about instead of focusing on multi-scale methods. So we're not going to talk about finite elements.
Very special case that you are given a job to do and do the same time what the job is.
Short answer is yes. Hydraulic fracture propagation. You're not going to see any finite volume method that can do hydraulic fracture propagation. I've never seen. Have you seen, Harun? Never seen. So that's where finite element methods thrive. Geomechanics originally was just finite volume. Was originally just finite elements mostly, but people have figured out how to get to model coupled flow and geomechanics even with finite volume. In MRSC, there are modules for that, but nobody has been able to do fracture propagation with finite volume methods. So momentum is like a statement of, that's the equation is a statement of conservation of momentum, and finite volume method can actually conserve flux across the interfaces locally. But so finite volume method is known to conserve mass, right, locally. Finite element method, if you go through the derivations and you look at all these conjectures that have been proposed for finite element method, what it conserves locally is energy. So you see it conserves half K, whatever. So it conserves energy locally. And that's why it's useful in geomechanics, because you want the energy to be conserved. When you're doing fracture propagation, it's basically dissipation of energy when you exceed a certain criteria. So it's just unique to the formulation. The formulation is different and is more suited to mechanics, like fracture propagation, geomechanics, induced seismicity, right? Those are the kinds of situations where you need finite element methods. And people have coupled it with finite volume. So you use finite volume for flow and conserve mass, and then you use finite element for geomechanics and fracture propagation and conserve energy. But there are some finite element methods. So everything I've said about finite element method is for the standard finite element method. There are some modifications to finite element method to make it conserve mass. Fixed finite elements, mixed finite element method. It's going to be solving two equations, one for pressure and one for velocity. And then it makes the system mass conservative locally. Discontinuous Galerkin finite element method. The standard one is Galerkin finite element method. The discontinuous Galerkin conserves mass locally. Control volume finite element method, as you can probably guess, constructs a control volume around the finite element meshes, and it will conserve mass locally in that control volume method. And I've actually published on this. This is what I did for my master's. Why did I do this? So that the centroids of the control volume will be at the nodes. And then when you are doing the geomechanics, the solution for the displacements are the same nodes. So the location of the pressure and the displacements are co-located. That was the advantage of doing that. So you will see this also in the literature. But none of these, we are not interested in any of this in this course. This is the guy we are focusing on, finite volume methods. Finite difference method. Looks like I've discussed this before, or maybe that was in the video I recorded. That's your question? Okay. This is your single phase flow equation, right? If you discretize this and then express it in matrix form, you have this. If you guys are interested, I don't want to overwhelm the module page with all sorts of materials from 4056, but I actually went through the process of discretizing this for multi-phase flow and then obtain these matrices. So what is X? Solution vector, right? Pressures and saturations for two-phase or three-phase. What's T? Transmissibility matrix is basically taking the contributions of K, A over mu in your That's the part. It's basically everything here. So that when you do TP, it's equivalent to evaluating whatever is here. That's what TP is. Where P is vector, this is matrix. B is your accumulation matrix. It's taking into consideration everything here. And then, of course, X remains your solution vector. And Q takes into consideration whatever is here. So it's just a matrix form of the discretized system of equations. And you will see what I mean by that shortly. Again, our focus is not finite difference method, but let's simplify this problem. Let's assume rho K over mu gets us 1. So if rho K over mu is 1, then the system becomes this. And then we assume a steady state, so we neglect the mass accumulation term. So Laplacian of P equals Q, that's what you have. Poisson equation is the simplified name for that, and we wrote that out before. If you change Q to 0, then it's Laplace. But this is Laplacian of P. So how do you discretize the 2p dx squared? If you avoid the videos I talked about on the different discretization schemes, or you just follow the steps here that I laid out, you would have figured out, if you follow these steps and you obtain the second order approximation of the central difference scheme, this is what you get straight up from Taylor series. So the 2p dx squared is this. And that's equal to qi. What are the i's? Grid block number. So if I is 1, that means you're sitting in the first grid block. This is what you get. I is 1, right? So I plus 1 is 2, I minus 1 is 0. If I is 2, I is n. Actually, I is n minus 1, so that you get to n and not n plus 1. So those are 3 systems of equations. So what you're solving for is a system with 3 grid blocks, 1, 2, 3. And this is the equation. 1D flow, right? So how do you solve this system of equations? So what I want to achieve here is to show you how you can move from equations. These equations are simultaneous equations, right? To matrices. And this is significant. You need to know this regardless of the discretization scheme. If it's finite volume, finite element method, and you have systems of equations, this is exactly what you will do. So move from equations to matrices. And you should also be able to do the opposite. You should be able to look at these matrices of the matrix form of the equation and figure out what the simultaneous equations are. So these are the 3 equations for the 3 grid blocks, but I continue all the way to 6 grid blocks. So I assume you have 6 grid blocks. From the pattern of the first 3 equations, we can figure out what all the other equations should be for grid blocks 2, 3, 4, and the other ones I didn't list. So it's always A x equals B, right? So this is your A, matrix A, vector X equals vector B, right? Matrix vec, math vec, will always get you a vector. So you already know the procedure for doing matrix vector operations, right? This is linear algebra. You're going to multiply the first row, right, by the column. Everything in the column, right? So it's minus 2 times P1 plus 1 times P2 plus 0 times P3 plus 0 times P4 plus 0 times P5 plus 0 times P6. That's the left-hand side of equation 1. And that's going to be equal to right-hand side of equation 1. So that's how it works. So that multiplication that we just talked about gets you this. And you can convince yourself that that is the case. Take this 1 over h out. 1 over h squared. So all you are left with is this P2 minus P1. So the term that will be here has to be the coefficient of P1 in your equation. What's the coefficient of P1? -2. So you put -2 here. That's how you construct the matrix. If this is not clear, please raise your hand. This is what you need to really absolutely know. Now, you want what's the coefficient of P2? The term that's going to be here. So you come in here, it has to be 1, right? That's why there's nothing there. So you put 1 here. What of P3? It doesn't exist in that equation, right? So 0. Same for P4, P5, P6. But there's PO here, P0. But there's no grid block 0. So what do you do? It actually, huh? Yeah, it's basically a boundary condition. So it's a constant. You're not solving for it. So you have to take it to the right-hand side. And it's going to be part of your source term. So it's P0 over h squared, right? Because you say 1 over h squared here. So take it to the right-hand side. So you have Q1 minus P0 over h squared. Isn't that what we have here on the right-hand side? First term here. Can you all see that? So that's why this is P0 over h squared. And then you do the same for the second equation. 1 over h squared is already outside. Qt is going to be on the right-hand side. So you need to only worry about this. What's the coefficient of P2? -2. What's the coefficient of P1? 1. Coefficient of P3? 1. So that it's 1. So remember, you're going to be multiplying all of these second row by the same solution vector. So it's 1 times P1 minus 2 times P2 plus 1 times P3 plus 0 times P4 and so on equals Q2. That's the equation you've written. And you can continue to do that for all of the grid blocks through P6. In P6, you need a boundary condition just like you had here. Same deal. And then how do you solve AX equals B? Linear algebra. We're going to take all of that like mathematics is just a tool for solving it. We're not going to spend time on that. But what you will do will be inverse of A times A, multiply both sides by, pre-multiply both sides by A inverse. Pre-multiplying and post-multiplying don't give you the same thing, right? A times B is not the same as B times A. So you have to say whether you're pre-multiplying or post-multiplying. You're pre-multiplying both sides by A inverse. And what's A inverse times A? So it goes away, right? And X is A inverse B. So that's what the direct solvers do. They implicitly invert A somehow. But inverting A exactly is a pain. And the system may be ill-conditioned. And the condition matrix may be too high. And you don't want that. So what you will do is you do a pseudo inverse that's approximately equal to the inverse. And in MATLAB, what you will do is actually just A equals X equals A backslash B. And let MATLAB worry about the best algorithm to solve the matrix you have provided and the vector you have provided. So if you do this in MATLAB, you're done. You don't need to worry about this method it uses. It will figure out the best method to use. And there are different options. You can use direct solvers. You don't have A backslash B in C++, no. But there are solvers in C++ that you can use. There is PETC, a massive solver. There is Aztec. There's so many, 3Linux, so many packages with different solution methods. It's up to you to figure out which one to use to solve your problem. And then there are solvers that have been used for reservoir simulation. These guys have been used. I think Eclipse uses nested factorization with the option of GMRes, generalized minimum residual method, by conjugate gradients method. TOF does BICG. And then there is also BICG style. It's A/B. I corrected that on my slides, but I've not updated it. It's matrix \B. The matrix has to come before the vector. You can try it, put a matrix and put a B in.
In this direct solver and linear solver, which one is faster? Doesn't matter.
It matters depending on your A.
Oh,
If you provide an A matrix that is 1 million by 1 million, and you go use the rest solver, you will see it may not be possible to solve it. 1 billion by 1 billion, it will never be able to solve it because of memory. Direct solvers will converge in a fixed number of iterations. And I have videos on that in Petty. If you want to go through the pain, yeah, I've done that for small systems. I actually do it in Excel, and you can play with it and see how direct solver works. It will go through a certain number of steps, and you will always get the answer. But the problem is, it's memory intensive. It requires a lot of memory. So you only want to use it for small problems, 20 by 20, 50 by 50. You don't want to use it for 1 million by 1 million grid blocks. So that's when you must use an iterative solver. So the iterative solvers will converge. Some will converge faster than others in certain physical regimes. So depending on the problem, they converge faster than others. And then these are different options. And they're all Krylov subspace solvers. And then the mathematicians, applied mathematicians, they keep working on different solvers and they keep optimizing them. You have to, if you want it to be faster, sometimes you have to do preconditioning to precondition the system. You see in Eclipse, they came up with CPR, constraint pressure residual, for preconditioning so that it's more stable. And we saw lots of improvements. Before that, when you have three-phase problems, in certain cases, it's harder to converge. So, and then you can parallelize that, like I said. And PETC is a parallel library, which is very robust. It's like, yes, but that one is commercial. So if you graduate from here, for everyone or for students?
I think for everyone, starting 2021, yeah.
Oh, okay. That's nice. So different solvers have been released. Intel is highly optimized. So if you use that Intel on Intel processors, you will get.
But at this stage, most of these solvers you have to use, like, if you are running like it's a compiler, let's say. For example, if you are running Fortran or C++ in let's say code block.
In what?
Code block.
That's an IDE, right?
I mean the compiler, different compiler.
Yes.
Compiler.
Yeah.
The library doesn't work.
Yes. Yes.
So that's the problem.
Yeah, that's the problem you will face. So if you want to use Intel's tools, you want to use it on Intel compiler using Intel processors. If you start taking Intel stuff and you want to use it on AMD processors and stuff, or a different compiler that is not optimized for the kernels in Intel, then you don't get.
I don't know if all the high performance computer, I mean, very sure has Intel compiler there, that's okay. But what about if you are working in a company that doesn't have Intel compiler?
Let's see. Yes, that's why I wouldn't even think about it. I know there is Intel stuff. I don't care. Just focus on one that is robust, and that's Betsy. That's one of the most advanced, and it's open source, and it will compile anywhere. To compile on your Unix, on your Windows, on Intel, on AMD, on ARM, whatever stuff. Betsy is very robust and powerful. Ah, yes. PETSC. Parallel Extensible Toolkit for Scientific Computing. I think that's what it is. By which national lab is that? It's Argonne National Lab. Very powerful, very flexible. You can customize it. You can select different compilers at runtime. That's the power. So you can test different things and figure out the optimum solver for your problem. Finite volume method. Integrate the equation. We already did this, right? Right on the second slide, I believe, in this chapter. Just integrate everything over control volume. And then for the second term, use divergence theorem. Convert from volume integral to surface integral, you get this. And the next thing is, how do you integrate the first term? It's like integral of k dv. What's integral of k dv? kv, right? And that's what you do. This is your m. So I haven't integrated yet. This is where I integrate. This is basically your k times v. After integrating it, that's what you get. How about the last term? Exactly the same way. Rho q is your k. The middle term is the one you work a little bit for. So this is f, right? For flux. It's now a surface integral. And then integration is basically summation. Well, you can approximate integration, which is a continuous operation, with summation. So if you sum across all of the surface that bound a control volume, that's what this integration over the boundary is. The boundary of that control volume. So this control volume is bounded by how many faces? 5, right? So you want to integrate over each of these 5 surfaces. All you do is to sum the flux coming in across all 5 surfaces. That's what this is. So NF will be 5 for this grid block. Number of faces. Yes. Can you say that again? This guy is what? No, yes, it's just like a variable. Like I mentioned, in some mathematics literature, they don't even put this there. You already told us you're integrating over omega, so we don't care whatever variable you put. So some puts this the x there. X is a vector, a space vector. It's not x in one direction. That's why I made it bold. But some people will do the omega. That's what I actually used to do. So it looks like integration of something dx. What you're integrating over is the domain. So you can use dx, you can use the omega, or not use anything. You already told us what you are integrating over. So again, the important thing is this continuous integration is approximated by summation over all of the faces that bound the control volume. It's an integral over the boundary of the control volume. So it's a summation. And what are you summing? The flux is multiplied by area. And what's flux multiplied by area? Talk about that. What's flux times area? Huh? No. Right? We've talked about it before, so someone has to figure it out. It's mass rate, rho AV, right? Flux is rho V. So rho V times A is rho AV, mass rate. So each term here is actually mass rate. And remember what I told you about this guy, depending on the unit of Q. I don't have to keep mentioning it every time. When you do the unit conversion, you will see it actually should be rho Q. Now, if Q is volume per time. So if you ever work this out and you see that your rate the unit on this term is not working out, divide by Q. How do you get F? And the reason you see this, I should mention, is that different authors use different units for Q. That's why the equation is always messed up, this guy. So if the Q was written in kilogram per second per time or whatever, then you may not need to divide by. That's where the confusion comes from. So, and then when you are writing your paper, you need to tell us what your unit for Q is. And then some people have used volume per time and they forgot that they need to divide by volume. So that's a common error. But whenever you're writing a code, you will see you have to do dimension analysis. Don't just write code and never do dimension analysis on the terms and just hope for luck. You will never have luck when writing code. That's what you realize. It's scientific computing. There's no luck. If you don't think about it and work the unit, it will not work the first time. It never does. It never does work the first time. So you want to do the dimensional analysis, be sure, okay, you've converted this to the right unit and then this to the right unit before you even implement. Otherwise, you'll be struggling and looking for bugs all over the place, whereas it's just unit conversion. So it saves you a lot of time when you do the unit dimension analysis, consistency check before trying to analyze the results of your code. How do you get F? Flux, right? Rho V. You already know the equation for V. That's the equation. Multiply by rho. That's what this is. You don't have to. You don't have to. Yes, for gas, you don't have to. Actually, when I write my codes, I don't. Just implement density. Let the code calculate density. You don't have to replace the equation with the expression for. That's what I will do. That's what we do in numerical simulation. Is if you want some simplistic approximations and then you put all of the equation and you're substituting and changing the governing equation, you don't need all of that. You want your code to be generic. If it's for gas, go in there and in your compute density function, then use PM over ZRT. And then you go create a function that will compute Z from the equation of state and then calculate PM over ZRT.
But if about this one thing that always check the previous times the pressure, right?
No.
Let's say if you want to calculate pressure at current times, we know in the equation that we need pressure to calculate density.
Yes. Yes.
You don't have to.
You don't have to. If you use the previous time step, that's lagging coefficients. So remember, we're going to do fully implicit. In fully implicit, you never use, that's why I said, remember, all the other terms is at n+1, it's current time step you're going to use. But what you're going to do is current time step, previous Newton iteration. Remember, there are two loops. So you have the pressure at the current time step and at the previous iteration, the iteration you're working on, the Newton iteration you're working on. Yes. So you always use the current stuff. It's just a second loop going on. That inner loop, you are solving for the delta X. So in that inner loop, you're solving for the delta X. When you get the delta X, which is delta P, which is single phase pressure, add that delta P to the pressure you had before. Then you've updated your P. Have you converged? If you haven't, we're going to do all of that today. If you haven't converged, then you go to the next Newton-Raphson iteration, but you are the current time step. Yes, that's what you will do. So pressure at n+1, comma P. That's the Newton-Raphson iteration. That's what you will use in this compute density function. And it's generic. So if you want to calculate density for water, implement compute density for water, go use whatever equation you want for the water density. For oil, use another equation. So that's how everything is the same governing equation. You don't have to go in there and start substituting equation of states and all of that, so that you have something in terms of pressure. No, in the nonlinear sense, if you're going to solve with a fully implicit solver, it's not a good idea to go in there and be making all these manual substitutions that were developed originally for well testing and things like that.
Yes, I tried to get
Exactly. That's exactly what happens. Yes. That's exactly what happens. Some people have tried to write a simulator based on the pressure squared approach. But if you remember pressure squared approach, that was, is it Aluseni? No, Aluseni is the pseudo pressure stuff. But those are all based on analytical stuff, well testing, analytical solutions. So you're trying to simplify it so that you can solve it with a simplistic solver. But when your equation is non-linear, just implement it as is. You're going to use a fully implicit method. And that's where the Newtonian iterations come into play. So Newton-Raphson linearizes the nonlinear equation for you. That's what I just described. This inner loop is linearizing it. And then you can solve it for the change, and then add the change to the previous pressure. And then you keep adding it until you have tested that you have converged. And we'll talk about convergence tests. After you converge, then you have the final answer for P. You've taken multiple delta P's. And then you find the final value for P at that current time step. Then you go to the next time step.
I want like, we are looking for you to have some every iteration in the solutions form. So it's not the actual question, it's a guess question until you converge.
Exactly.
Yeah. So I was thinking like, okay, if I use the long pressure calculus and then do calculation, it might not even converge. That's what I was thinking.
Yeah, it will converge as long as your initial guess is close enough to the, and it usually is, right? That was the starting point. Initial pressure was the same everywhere. And then you've added a well and you've taken out some pressure. And then the system converges actually. Yeah, it converges. That's how all these multi-phase simulators are implemented. You're going to see that in MRST. That's how it's done. And these days, we're having more and more open source on reservoir simulation. Back in the day, there was nothing. MRST was the first one. And then OPM, which is a pain. It's in C++ and all, it's a pain, but there are more open source stuff. There's GOSX now, which is also very robust. There are many open source codes. So you can see this is actually how they implement it.
I think, I don't know if people developers that simulators develop the back or there's my little experience. I think because my rate of the time done by so many years.
It depends.
They actually say so
Yeah.
and it doesn't matter if MATLAB, Fortran, or C++, or Python. At the end of the day, the linear will be the same. There is no linear call it fashion.
Yes.
So what's the point of choosing programming language to develop something?
That's a philosophical question, and it depends. So people say most of the time is spent in the solver. It depends, right? In that paper, he was looking at a certain type of problem. If you come to if you start solving multi-physics problems, you will see that it takes a long time to compute the Jacobian. So it's not every time that all of the time is spent in the solver. It depends on the system of equation. When you start to do compositional stuff and you're flashing, if you have 20 components, and you try to calculate the Jacobian, you will see you're not going to use 70% of the time in your solver.
So if you have 20 components, you will have
it depends on the number of, so number of equations times number of grids is the total system. So I'm just talking about the number of components, and then few grids. So the solver time will be fast, but the assembling the Jacobian matrix will take a lot of time. Yeah, it's people say different things, right? But what they are saying is consistent with what they are working on. So if it's doing two-phase flow or single-phase shale gas simulation, and it's saying 90% of the time, because you can spend 95% of the time in the solver too, depending on the kind of system you're working on. So if you're doing single-phase shale gas simulation, right, single-phase, and then you have 1 million grid blocks or 20 million grid blocks, yeah, almost all the time, 95% or 98% will be spent in the solver. So it depends. But the question of which code you're going to use, which programming language, is going to be up to you. How good are you at C++? If you're extremely good at C++, that's what you want to use. The advantage of C++ is it's faster. But his point is, well, most of the solvers are in C++ anyways. So for the average petroleum engineer or average engineer, it's easier to learn Python or MATLAB than C++, which is a pain if you really want to go, if you want to do it right. It's a pain to learn how to do it right. But there are different open source packages. If you find an open source package that can solve that has some framework that you need, and it's implemented in C++, you will want to do your code in C++. If you find an open source package that's implemented in MATLAB that we did and has many of the things we want, it has compositional simulation, and we're trying to do compositional simulation for fractured reservoirs, then we did it using MRST. So there are going to be different tools out there. But for me, what I think is most important are the things you don't want to do yourself. You don't want to write a linear solver yourself. You don't want to implement Krylov subspace. I don't know anyone who has. I don't know any graduate student who has successfully implemented a Krylov subspace solver. Yeah.
I tried. When you test it for like 10,000 by 10,000.
Simple problems. Yeah. Yeah.
Become 10,000 by 10,000. It becomes extremely small.
Yeah, because you're going to implement the easiest solvers like Gauss Seidel, those simplistic ones. That's the thing. If you want to do these more complicated stuff by conjugate gradient stabilized, yeah, I've worked on that one before with a friend. It worked, but again, it's not going to be robust for everything. You're not going to be able to do all sorts of preconditioners. And that's what you need for real industry problem. After writing the solver, you have to figure out the best preconditioner. That's also a whole course in matrix computational linear algebra. So don't do it. You have other issues to worry about. We are petroleum engineers. We understand the governing equation, and if I see the results, I can infer what's going on. That's what should be your strength. So in general, what I look for in a system, they have to give me easy access to solvers, like PETC, everything is connected, fast solvers. And the other thing is AD. Many people don't worry about that, or they're not very familiar with it because it's a new concept, not that new anymore. Like 10 years, it's been around for about 10 years now.
Yes.
Yes.
I just know about this from TensorFlow machine.
What is AD?
Automatic differentiation. We are going to get there. So I think we are getting ahead of ourselves, but it's good if that's what we're interested in. Yeah. Automatic differentiation or algorithmic differentiation. And you will see exactly why. Let me move forward a little bit and let's get there, then we can talk more about that. But we already got to this part. So again, this is what you don't want to implement yourself. So if your system has AD and it has solvers, very easy to write simulators. Give me any problem, any PD, I can solve it if you have AD and solver in there. I can solve it in weeks. But if you don't have those two, it's a pain to set up the Jacobian, it's a pain to write a solver yourself, or you will use a weak solver that will not be able to solve anything robust. So that's where we are headed, actually. So those are all good questions. We already talked about this. So finite volume method.
Can you explain that term QV? That was just the integration of VX.
Yes, I basically took out the V. Why? Because remember I pointed out that if you do dimensional analysis, you should have been rho QV before, so that when you integrate it with the V, then it becomes rho Q. So rho Q is just flow rate. It's your source term, your well rate. And we're drawing a certain volume from the reservoir per day, and you just go take it out from that grid law. And then the other terms will change, and then the pressure will change to get you a residual equal to 0. So that's the forcing function. You remove components or remove fluid, and everything changes, the pressure changes to make the residual 0, and that means the pressures actually drop. So that's the rho Q. Good. So this is the finite volume method, but there's nothing really about, we are continuing the finite volume method, but there's nothing finite volume about this. This is actually focusing on how we get the Jacobian. So it's Taylor series, right? This whatever I'm going to talk about here works, whether it's finite volume, finite element, or finite difference. So what are we doing here? Find Taylor series expansion of R at k plus 1. K plus 1 is a time step. We used to write it as n plus 1 before, but here it was changed to k plus 1. So same deal. X plus delta x, solution variable for plus change in solution variable, and x's are what? Vectors or matrices or scalar. What is it? It's a vector, correct. It's your vector of solution variable. So pressure in grid block 1, saturation in grid block 1, pressure in grid block 2, saturation in grid block 2, and so on for two-phase oil and water. So it's an enumeration of all your primary variables going from grid block to grid block. So this is the same Taylor series expansion. This should be clear to everyone, right? The only part that may not be readily clear to you is that this guy, what do you think this will be? A vector or a matrix or a scalar? You are differentiating the residual, which is a vector, right? With respect to another vector, each of the vectors. So that actually gets you a matrix. So this is a matrix. It's a matrix that contains derivatives. The derivatives of each of the residuals with respect to each of the primary variables. A matrix of derivatives is called what? If nobody knows the answer, then nobody has watched the video I uploaded. Jacobian matrix, you watched the video? Good. Matrix of derivatives, Jacobian matrix, you must have been hearing that the Jacobian is just a matrix of derivatives. That's all there is to that. You see any matrix and it's filled with derivatives, Jacobian matrix. So that's what this is. How did we get this term here? So this is the residual at the current time step. Whenever it is accurate, it should become 0. Because the residual, how did you get the residual? You took all the terms to the one side, to the left-hand side, and it should be 0, right? That 0 is actually residual because it will never be 0 in a numerical scheme. You have round-off errors, you have truncation errors. It will never be 0. So it will be equal to the residual. So that's what this residual is. The goal is to make this residual equal to 0. So we can set that to 0. So unless it's only these two terms. So what's the expression for this term here? Just take the other one to the right-hand side, minus residual. So the Jacobian times delta x equals minus residual. And that's the equation we solve. This is what linearizes your problem. Because you're solving for changes in primary variables now. And I will go deeper here. This is how you will solve it. I fixed the slide. It should be minus Jacobian / residual. So let's talk briefly about what this will look like for an actual system. Because we've said this is your Jacobian. So the system you're solving is now Jacobian delta x equals minus residual. And that's the solution, J/R. So let's find some space. We can write out Jacobians. We already know it's a matrix of derivatives. You can watch the video I uploaded, but I'll still talk about it briefly. I'll start it and you will see the pattern, and I'll just stop. Immediately you see the pattern. There's always a pattern to it. So J delta x, this is J, that's delta x equals minus residual. What if we write the residuals first? You have to write the residual for each of the equations in each grid block. So let's assume it's two-phase, oil and water. So pressure, oil pressure and water saturation. I'm just going to use P and S. We already know the P is for oil pressure and saturation, grid block 1. So you can put subscript 1 there. But that's not what should be here, right? What should be here? Residual, right? So residual in grid block 1 of the pressure equation. Residual, you're still in grid block 1, saturation equation. Then you move on to the next grid block. Residual, grid block 2. Residual, saturation equation, grid block 2. So everybody can fill up this stuff, regardless of how many. So at the end of the day, what you have is equations for all of the grid block. So it's a list of simultaneous equations. We are writing the equation in matrix form, the way we illustrated for the P1, P2, P3. That's what we're doing. So is that clear? So we have just written out the right side. The right-hand side is residual of the first equation in the first grid block. Residual of the second equation, which is saturation equation, in the first grid block. If there were three primary variables, you will write the residual of the third equation in the first grid block, and then you go to the second system. So any multi-physics problem they give you, that's how it will be. If there are 20 equations in each grid block, list all the residuals for all the 20 equations, grid block 1, and then repeat this block structure, and keep going. So the right-hand side is straightforward. This delta x is also straightforward. It's also a vector, right? So delta what? P or S? The first equation is a pressure equation in grid block 1. Delta what? What's the next one? And this is, and so on. So you already get the structure. So now you're only left with the Jacobian matrix. I took 2 courses on reservoir simulation. I still didn't understand this stuff until I took another one where we actually implemented the code. The first one, we're given seed codes. It could calculate Jacobian, and it was calculating it. And nobody calculates the Jacobian as a matrix because it's a waste of time, as you will see. It's mostly zeros. It's sparse. It's sparse. The number of non-zero entry in each row is the number of neighbors that stuff has. So nobody starts it that way. So if you have a complicated code that is already set up to calculate the Jacobian for you, you just use it. You never know the structure of the Jacobian. Until I programmed the Jacobian myself, I didn't know. And then after I programmed it myself, I figured out why you don't want to program it yourself. That's why you want to use AD. So AD will give you this Jacobian, and it will be optimized. It will only be sparse. That's why you want AD. So let's talk about what it will be. So let's start filling it, and then we'll talk more about what is in there. It's the R, the X, right? The first equation is what you are writing out, right? Grid block equation for first equation in the first grid block. So the residual, what's the first equation? Is here, right? R1, P. That's what you're going to differentiate with respect to all of the primary variables. So that means I should point out that row 1 is always the first equation, right? Remember, equation 1, that's row 1. Equation 2 is row 2. So we want to construct equation 1. So it means we need to fill up row 1 here, right? We mentioned it's always row 1 multiplied by the solution vector. Down. That's what gets you the left-hand side of equation 1. So since we already know that we are going to always be differentiating this residual, you can figure out the numerator for all of the terms here. It's always residual in grid block 1 of the first equation, which is pressure equation. That's the numerator in this derivative. It never changes on this row. So that's what you should know. Now, what are you differentiating the first one with respect to? See this guy? P1, right? So the first primary variable in the first grid block, P1. What's the next one? S1. This is the P1. So the RP1, the P1 is what is the first entry. First row, second column. The R1, the P, the S1. And what's this one going to be? You have moved on to grid block 2. So it's what? And this one is what? And what's its numerator? R1. What's a P, right? That never changes. So if you've understood this, that's what took me like 2.5 years of grad school to figure out. Because nobody explained it this way. They just talked about the Jacobian matrix and adults programming different properties. Is what? Right now, I'm writing it for all of the terms. Most of it will be zeros at the end of the day. If I continue and I write it for 100 grid blocks or 1,000 grid blocks. Yes. This is the equation for everything. It will turn out that most of the derivatives will become zero. Because if you differentiate the R1P with respect to grid block 20, and grid block 20 is not a neighbor of grid block 1, it will be zero. Because you're differentiating something with respect to another variable entirely. So that's why it's sparse.
I asked this question because I was thinking that we have symbol P1, delta P1, and then we go the symbol P1, delta P2, and then we have the dot showing that we are continuing for all.
So this is one. Then you can have dot after this one. Then you go to the R1P. So this is what repeats for all the grid blocks. But you will write it all out, most of them will be zeros. The ones that will be non-zeros are the ones that are neighbors of grid block 1. So they contribute to residual of grid block 1. If it's not a neighbor of grid block 1, it will not contribute to its residual. Now, that's equation 1. What's equation 2 for? It's for the residual of the saturation equation, the second equation, still in the first grid block. So what's this going to be? Who's going to tell us? D RS in superscript what? 1. With respect to the P1. Good. Some people have already caught the pattern. So the pattern is this numerator here will be the denominator here will be the denominator here. The denominator here will always be the denominator here, so you can as well write them all out. Because it's the same ordering for the x's. And that continues. And then you already know the numerator never changes along a row. So this, the RS one you guys already got, will always stay the same throughout. And then you are done for grid block 1. Then you move to grid block 2 and do the same kind of stuff. The pressure, saturation, and so on. And you can watch the video again. But what you should do is, can you write out this matrix, what I did here now, for 3-phase, pressure, SO, SG. If you can do that yourself, then you'll have cemented this knowledge. And then any code you see, you just see the Jacobian, you already know what's going on. Some of the things we use in our research group, trying to get the derivative of fugacity with respect to pressure, with respect to XI, mole fraction, extremely hard to try to compute yourself. But if you understand this stuff, then you can ask MRST to do it. And then you know where the different derivatives are based on the structure of the Jacobian. So understanding this is actually key. Good. So this is the Jacobian matrix. You can see it's a matrix of derivatives. Now, how do you calculate it? Easiest way, write a loop, and I can share the code. Yeah, I will actually share the code if it's not already shared. That you can give me any x, and I can perturb it and get you. I can perturb it and get you your derivative. What is perturbation? Leibniz rule of differentiation, right? So if you want to get the R, the P, for instance, we'll go perturb P. R at P plus delta P minus R at P, right? Divided by delta P. That's what perturbation method is. So you already know, anyone is taking it up. You already know P, right? At the current iteration and correct iteration. Okay, multiply it by 1e minus 8, something very small. That's the perturbation. So when you have perturbation method, that's all it is. There's nothing, it's just a fancy word. Just add delta P to P, you have perturbed P. And then go find the residual at that perturbed P. You will have written a code, a function for residual. So you call it with P, that's the residual at P. You would have done that already to get the right-hand side. To get the Jacobian, right? I hope that part is clear. To get this guy, you have called a residual function that you've written with P. Now, do P plus delta P. Delta P is 1e minus 9 times P. So you have a value for P plus delta P. Now call that same residual function with P plus delta P. That's the perturbed value of R. That's this. And then you already have this divided by the perturbation. That's your derivative. That's how you get one item here. So brute force approach, you will write a function that will take this residual, right? And then perturb all the primary variables and just form this matrix. It will be forming it row by row or column by column, depending on how you set it up. The problem is brute force, right? It will get you this stuff and it's scalable to work. If you change it to 3 equations per grid block, it will perturb everything and it will still fill up the entire Jacobian matrix. It works. Problem is perturbing everything. It's assuming that all of these guys will not be non-zeros. So it will perturb it and later realize the answer is 0, but you already incurred the computational cost of calculating it. So that's the code that we all write as graduate students when we work on it. You just perturb everything and get your Jacobian matrix and you're done. But that's not what commercial simulators do. They know the indices that are going to be non-zeros. They will not perturb those. Those commercial simulators based on perturbation method, like TOF. That's what they do. They know the sparsity pattern of the matrix, and they only go perturb in those grid blocks that they know will be filled up because those grid blocks are neighbors. Because you now know where the grid blocks are, right, based on this structure. So you know the ones that should be non-zeros. Those are the ones that are neighbors of grid block 1. For grid block 2, it's the neighbors of grid block 2 that will be non-zeros. So they only perturb in those guys and then get the Jacobian. If you try to program that logic, you will see it's a lot of pain to try to do that based on the perturbation method.
They're calculated by indexes or trying to tell which one are zeros and which one are.
Yes, so there is some non-local indexing that you will come up with to figure out based on the grid that you've taken in. You know, the grid can be unstructured because this is finite volume you're looking at. So that's why it's complicated. If it's Cartesian, regular grids, you already know the neighbors, east, west, north, south, and then you can program and perturb only that. That one is easy. Yes. So,
For network modeling, for example, you never know the pattern.
exactly.
One port will be connected to another port somewhere else. So
Yes.
know, but in Cartesian, as you say, you see that
Yeah.
there's a pattern that you do.
Yes. And in unstructured grids too, in reservoir simulation, same thing. You never know the pattern until you read the grid block. Then you figure out the pattern. In your poor network, after you read the poor network, then you know the neighbors. Same thing. Yes.
So in case of poor network, how do you perturb that connected force?
So you just get the pressure in the neighbor and perturb it.
But like in which direction you perturb the network? How do you?
The direction of the perturbation?
Yeah.
You can always choose a positive value. I'll always add delta P. So P plus delta P. Yeah, that's fine. Sign is not important because if you do P plus delta P and you're dividing by delta P, you're fine. If you do P minus delta P and you're dividing by minus delta P, you get the same result. So the sign is not important in the Jacobian computation. But now we've talked about only one method to figure out the Jacobian. Some simulators use that, but that method has its limitations. What are the limitations? Exactly what you saw when we sketched this. This is the limitation of your perturbation method. If this is the exact difference, and you're using plus delta P, so forward difference perturbation, is this slope? How well does it approximate this? How big of delta of this delta or delta P did you take such that now your slope is far away from the value you want? That's the problem with perturbation method. It carries truncation error, and you'll never know because nobody's going to give you this shape for your residual. It's your residual you're differentiating, right? You never know. It's a multi-dimensional stuff that you never see the face, you never know the function. You're just hoping in the limits of delta x tending to 0 according to Mr. Newton, it will approximate, but you never know. If this Jacobian if the residual is steep in that region, you will never get the Jacobian right. That's why you work with complex multi-phase compositional simulation, it never converges with the truncation error. That's why. So people have tried different things. So perturbation method is one. And you know what it is now, right? Leibniz rule, Newton's rule, whatever you call it. Whoever you prefer among Newton or Leibniz. I won't get into that debate. You know, some people believe Newton is the superior guy. Some believe Leibniz is, but they came up with differential calculus same time. Good, so that's perturbation method. What's another method? Who knows? Analytical Jacobian. So that's another way. You can use analytical method to calculate your Jacobian. What does that mean? It means you will go write out this expression for the residual, right? Based on the mass accumulation term, the flux term, and then you will differentiate it by hand. You say, okay, this is the equation. Say this equation, right? This is my residual equation. And then I put it to the left-hand side, equals 0. That's your residual. So residual is equal to that. So now you want to differentiate residual with respect to, say, pressure. So you grab this term and differentiate it with respect to pressure. So you need to know the derivative of density with respect to pressure. You need to know the derivative of porosity if it is a function of compressibility and stuff. If in density, viscosity, you need to differentiate that. And it's easy for single phase. A little moderately easy for the derivative with respect to saturation. It's harder. Huh? It can be done, yes. You will work harder for the capillary pressure stuff, but it can be done. Now, good luck trying to do this for compositional simulation. I thought it was impossible, but I realized GeoSX does compositional simulation and is based on analytical Jacobian. So some dudes have figured it out. So you can do it, but it's a lot of pain. It's a lot of pain to do. So that's the limitation for the analytical method. So if you are writing your own new, you want to modify, there's a library, GeoSX, and you want to add maybe a new physics. You just want to put in what you implemented in homework 2, sorption. You want to add sorption to GeoSX. So it's on you to figure out the derivative of your Langmuir isotherm with respect to all the primary variables, right? And you see that's pain. You may never be able to do that in record time. So that's the problem. Someone figured out the general equation, even modifications will be pain because you have to know the Jacobian or the derivative of whatever term you are putting. So that's why I don't like that. I don't want to have to figure out analytical derivative for everything I do. And I work with compositional simulation, so it's pain. That's the limitation of that. More accurate, faster. You have an analytical expression. You are not perturbing, you're not calculating residual twice. That's what you're doing in the perturbation. You're calculating the residual first at P, and then so it's computationally expensive. Here, after calculating the residual, just implement the function for the derivative, and you're done. So it's more accurate. So regardless of the actual derivative, it will get you the exact derivative, like I showed in that curve. It will get you that exact derivative at that point. So it's more accurate. But if you want to be extending, making modifications, you will have to be. So it will give you this exact derivative. That's the advantage, and it's fast. But a lot of pain to develop. And the last one is what we're going to be doing in this course. That's the one I like. And if you're like me, that's the one you're going to like too, because that's the AD, automatic differentiation. I can't find where I wrote it, but remember, perturbation method, analytical method, and then automatic differentiation or algorithmic differentiation. And then we have a whole slide on that, and we'll get into that when we get into MRST. But just to finish up this, after getting delta X, you already know what you're going to do with it. I talked about that. Update it, right? Update your X. This is your current iteration, previous Newtonian iteration. Same with pressure, saturation. And that's all on that slide. And then repeat. I provided this equation. This is one system I solved as a graduate student, and I want you to look at it and figure out the number of equations I'm solving and what do you think is going on. That's why I put it there. And you all can do that. If you can't do it, spend time on it and then look at what the video I uploaded on this section. So I won't talk about this here. Just look at the Jacobians, look at and then figure the pattern, and you can see the index. This changed to 2. So you can get your engraved of 2 now. And this is what I've talked about before. The loop from 1 to the last iteration, last time step. And inside that is your non-linear iteration, which is Newtonian iteration in this case. The other methods, other than Newtonian method, but in reservoir simulation, everybody uses this Newtonian method. So for delta x, if it converges, you are done. So you get out of this inner loop and you move to the next time step. If it doesn't converge, you repeat the inner loop until it converges. What is your convergence criteria? This is the most common, right? That's your error. The residual normalized by the mass accumulation term. And you want it to be less than the tolerance, which can be 1 e minus 5, 1 e minus 6 common values. This is what is mostly used in most simulators. If you are doing a toy problem, you can say whenever the delta x is small enough. So you can use delta x. If delta x is basically approaching 0, then why take another iteration? That's the logic. But this is more concrete in terms of conserving mass, because the residual is like an error in mass. And this is where we're going to stop. Any questions? Yes, that's exactly what it is. So you implement this. That's risky. So you don't know that the system converged and you're moving to the next time step. So it may not converge in 4 iterations, and then your error can blow up and you start getting on top and code. So you have to make sure it's actually correct. That you went 4 iterations does not mean it's okay. And then if you change it to 12 so that you can guarantee it to converge, then you're wasting time, right? That's a matter from attached. All right. So you really need to have this in there. Or the simplest one, delta x, just change your primary variable, make it less than 1 minus 5. It also works. I've done that before. But don't just move on. I think Arun has done that before too, right? You've done that before, right? You just go through several iterations and move on to the next time step. And it's not a good idea. It depends. So the kinds of problems you work on, sometimes it doesn't. At the beginning, it converges fast, and then later it doesn't converge as much. Then it also depends on the delta T you're taking and how big your degree block you're using. So it's never a good idea to write a code. If you do that in the industry, you will get a lot of grief from your manager. Yes. The class is over. If you don't have any questions, I see you guys are packing about, but you have questions.
Yeah, what was that term, the normalization?
Mass accumulation term. File.
What should it be less than?
Tolerance, 1 e minus 5. Common value, or 1 e minus 6. 1 e minus 5 is a good value. There are no questions. The class is over. We'll meet next class. And then we'll do quiz 3. Okay, so we're going to MRST. It would be a good idea you try to install MRST on your computer if you haven't. And we use the word install, but you're literally just copying a folder from MRST. You download MRST as a folder, you unzip, and then put it inside my documents or whatever you want to put it. And then go open up MATLAB and open up that folder. You're done. So we will talk about that in the next class.